Hello, and welcome back to Sleepy Wiki, your quiet corner of curious calm. Tonight we'll drift into a realm that hums beneath the surface of our modern world. A silent, pervasive force, older than cities, yet shaping every flicker of light, every whispered thought across vast, unseen networks. We'll explore a primal energy, once glimpsed in the dramatic brushstrokes of storm clouds or felt as a static cling from a rubbed piece of amber. An energy now tamed, flowing, giving warmth and glow to our quiet moments, and indeed, to the very pulse of life itself. Imagine tracing the invisible currents that dance between atoms, feeling the subtle yet powerful hum of something fundamental. It's a journey into the very fabric of how things connect, how they awaken and interact, not with urgency, but with a gentle, persistent flow that has always been and always will be. If these quiet journeys bring you a sense of peace, a gentle like or subscribe helps our little channel grow, inviting more weary minds to find a soft landing here. So, as you breathe softly, let us begin our quiet exploration of electricity. Let's turn our thoughts to the very essence of that invisible dance we call electricity. At the heart of everything we've imagined lies a fundamental property. Imagine, if you will, a vast, silent ocean, not of water, but of possibility. Within this ocean, every tiny particle, every atom, every whisper of existence carries with it a secret property, a kind of inner hum, a silent promise of connection or separation. This intrinsic characteristic, present in nearly everything around us, is what we simply call electric charge. Think of it like a fundamental personality trait for the universe's tiniest inhabitants. Some particles are born with a friendly, outward-reaching disposition, always ready to connect. We call this positive charge. Others carry a more reserved, inward-drawing nature, a negative charge. And then there are those tranquil, perfectly balanced souls, carrying no net charge at all, content in their neutrality. But the real magic, the profound secret at the heart of this electric ocean, isn't just that charge exists, but how it exists. Picture a vast, pristine beach stretching endlessly under a moonlit sky. You look down, and you see countless grains of sand. Each grain is unique, yet each is undeniably a grain of sand. Now, imagine that electric charge isn't like an endless flowing stream that you can divide into any size you wish. Instead, it's like those grains of sand. You can have one grain, or two grains, or 1,000,000 grains, but you can never have half a grain of sand. Not really, if you define a grain as its smallest intact unit. This, my dear listener, is the essence of something truly remarkable, the fundamental electric charge. It's the smallest, indivisible packet of electric charge that can exist freely in our universe. It's a universal constant, a tiny, precise unit of nature's electrical currency, never found in fractions, always existing as a whole, singular amount. Every single bit of charge you encounter, from the static cling on your laundry to the lightning flash in a distant storm, is made up of these exact, tiny, fundamental packets. It's like the universe's own microscopic Lego brick for building all electrical phenomena. Now, who are the primary carriers of these essential bricks? Mostly, it's two familiar characters from the atomic world, the electron and the proton. Imagine the electron as a nimble, tiny dancer, flitting around the nucleus of an atom. Each electron carries precisely one fundamental unit of negative charge. It's the universe's perfect little -1. On the other side of the atom, nestled deep within its heart, is the proton. This robust, steadfast particle carries precisely one fundamental unit of positive charge, a perfect +1. These two are mirror images, equal in the magnitude of their charge, but opposite in their polarity, creating a delicate balance within every atom. But how, you might wonder, did humanity ever come to understand something so incredibly tiny, so perfectly precise, and so utterly fundamental? This wasn't a sudden flash of insight, but a journey of careful observation and ingenious experimentation. Long before we understood the fundamental charge, we knew about the effects of electricity. Benjamin Franklin, with his kite and key, simply gave names, positive and negative, to the two kinds of electric influence he observed. But it wasn't until the early 20th century that a brilliant American physicist named Robert Millikan set out to truly measure this elusive, fundamental unit. Picture him in his laboratory, a place of quiet focus and meticulous work. He devised an experiment that, in its elegant simplicity, was nothing short of genius. He would spray tiny droplets of oil, so fine they were almost invisible to the naked eye, into a chamber. These droplets would pick up an electric charge, sometimes positive, sometimes negative, often by simply rubbing against the nozzle as they were sprayed. Then he would observe these tiny, charged oil droplets through a microscope, watching them slowly drift downwards, pulled by gravity, like microscopic dust motes catching the last light of dusk. Below them, he had two metal plates, one above the other, connected to a battery. By carefully adjusting the voltage between these plates, he could create an electric field, an invisible force, like an upward breeze, that could either slow down the falling droplets or even make them float upwards against gravity. It was a delicate cosmic tug-of-war, played out on a microscopic scale. Millikan's insight was this: if the electric charge on these droplets always came in whole, indivisible units, then the electrical force needed to counteract gravity would also change in discrete, step-like amounts. He meticulously measured thousands of these droplets, observing how much electric force it took to suspend them, one by tiny one. It was painstaking work, requiring immense patience and an incredibly steady hand. He found that the charge on every single droplet was always a whole number multiple of a smallest common value. It was never 1.5 times that value, or 2.7, but always 1, 2, 3, or some other perfect integer. This was the definitive proof. Electric charge is quantized. It doesn't flow like water. It comes in precise, individual drops. And that smallest indivisible drop, that universal Lego brick of electricity, is what we now know as the fundamental electric charge. Its value is incredibly tiny, about 1.602 by 10^19 coulombs, a number so small it's hard to grasp, but so universally significant that it underpins nearly everything we understand about the electric universe. So, as you rest your mind, consider this profound truth. Every atom in your body, every breath you take, every thought that flickers in your mind is built upon these fundamental units of charge. They are the silent architects of stability, binding atoms together, giving matter its form and texture. When these charges are perfectly balanced, an object feels neutral, calm, and electrically quiet. But when there's an imbalance, a few too many electrons or a few too few, that's when the world awakens with sparks, with attraction, with repulsion. That's when the static electricity makes your hair stand on end, or a tiny spark jumps between your finger and a doorknob. This interplay of attraction and repulsion, this dance of positive and negative, is a story for another moment. For now, let's simply acknowledge the quiet elegance of the fundamental charge, the bedrock upon which all electrical phenomena are built. It's a reminder that even in the vastness of the cosmos, there's a beautiful order in the smallest details, a universal consistency that allows the symphony of electricity to play on, and it's this very consistency that allows us to understand not just what charge is, but how it moves and interacts. It leads us naturally to the idea of charges in motion, a dynamic ballet that brings electricity to life. But that, my friends, is a tale we'll gently unravel next. And so, as we drift a little deeper into the quiet mysteries of our world, let us turn our thoughts to something as subtle and fleeting as a whisper, yet as powerful as a distant summer storm. Imagine, if you will, the gentle rustle of silk sheets, or the soft scuff of your favorite fuzzy slippers across a carpeted floor just before bed. Have you ever felt that tiny, almost imperceptible spark when your finger brushes a doorknob? Or seen your hair playfully lift towards a balloon after a gentle rub? These aren't magic tricks, dear listener, but rather the quiet ballet of static electricity, a phenomenon as old as the stars and as fundamental as the very atoms that make up our world. At the heart of this gentle mystery are the tiniest, most restless dancers in the universe, electrons and protons. Think of them as the fundamental architects of all matter, forever in a delicate embrace within every atom. Protons, snug and positive, reside in the very center, like the calm heart of a tiny solar system. And around them, swirling in vast airy clouds, are the electrons, nimble, negative, and ever so eager to explore. Most of the time, in every object around us, from your blanket to the very air you breathe. These positive protons and negative electrons are perfectly balanced. For every electron, there's a proton, creating a peaceful, neutral harmony. It's like a perfectly balanced seesaw, where no one side outweighs the other. But sometimes, with just a little coaxing, this balance can be playfully disturbed. This is where static electricity begins its silent, often unnoticed dance. One of the most common ways we invite this dance is through friction, a gentle rub, a soft brush. Imagine, if you will, two different kinds of fabrics, perhaps a wool blanket and a silk scarf, each with its own unique personality. When they lightly brush against each other, the electrons, those curious little wanderers, might find one material slightly more appealing than the other. It's like a tiny, invisible game of musical chairs. Some materials have a stronger pull for electrons, while others are more willing to let go. This quiet exchange, this subtle borrowing and lending of electrons, is known to scientists as the triboelectric effect, a fancy name for the simple act of rubbing two things together and having electrons jump ship. Let's bring this to life with a familiar image. Remember that soft balloon we talked about, and your hair? When you gently rub the balloon on your hair, the electrons, those negatively charged sprites, often prefer the rubber of the balloon over the protein strands of your hair. So a few of them, perhaps feeling a little adventurous, migrate from your hair onto the balloon. What happens then? Your hair, having lost some of its negative companions, finds itself with a slight excess of positive charge. The balloon, now carrying these extra negative charges, becomes negatively charged, and here's where the magic truly begins. Objects with the same charge, whether both positive or both negative, gently push each other away like magnets turned the wrong way. But objects with opposite charges, one positive and one negative, feel a sweet, irresistible pull towards each other. They yearn to reunite, to restore that perfect balance. So each strand of your hair, now positively charged, suddenly feels a gentle repulsion from its neighbors, causing them to stand up and away from each other, reaching for the ceiling in a whimsical display of invisible force. Meanwhile, the negatively charged balloon, feeling the gentle tug of your now positively charged hair, might mysteriously stick to it, or even to a wall, defying gravity for a little while. This dance of imbalance isn't limited to balloons and hair. Think of the dust motes, like tiny fairy dust, drawn to the screen of your television or computer. The rubbing of air currents, the friction of tiny particles, or even the electron-rich beams inside the screen can create a subtle charge on its surface. And when those tiny, uncharged dust particles drift by, the screen's charge can gently coax the electrons within the dust to redistribute, creating a temporary opposite charge, and poof, the dust clings, held by that invisible embrace, until a soft cloth breaks the spell. And even your clothes in the dryer, tumbling and rubbing against each other in a warm, cozy dance, can experience this static ballet. Different fabrics, like socks and sweaters, might exchange electrons, causing them to cling together, forming a temporary fabric-based magnet, refusing to part ways until you give them a gentle tug. This is why dryer sheets are so clever. They contain special chemicals that help balance these charges, preventing that clingy reunion. Now you might wonder, why does this charge build up on some things and not others? It all comes down to how well materials allow those restless electrons to move. Materials like metals are wonderful conductors. They're like superhighways for electrons, allowing them to zip around freely, making it hard for charges to build up in one spot. But then there are insulators, materials like rubber, plastic, or wool. These are like quiet, winding country roads for electrons. They hold on to their charges, not letting them move easily, which means that static charge can build up and stay put for a little while, waiting for an opportunity to balance itself out. And what happens when that balance finally wants to be restored? That's when we get the little surprises. The gentle spark when you reach for a doorknob, or the soft crackle you hear when peeling apart two static-charged items. This is called a discharge. It's the moment those built-up electrons, finally finding a path, rush to equalize the imbalance. That tiny spark is a miniature flash of light as the electrons leap across a small gap, briefly heating the air and causing it to glow. It's a very quick, very eager journey home for those wandering charges. On a much grander, awe-inspiring scale, nature orchestrates the most magnificent static discharge of all: lightning. Imagine immense clouds, towering castles in the sky, filled with countless ice crystals and water droplets. As these tiny particles are tossed and tumbled by powerful winds, they rub against each other, exchanging electrons, just like your hair and the balloon. The heavier, negatively charged particles often settle at the bottom of the cloud, while the lighter, positively charged particles rise to the top. The ground beneath the cloud can also become positively charged by induction. This creates a colossal imbalance, a cosmic tension yearning for release. And when that tension becomes too great, the electrons from the cloud unleash a spectacular, brilliant flash, leaping towards the ground or another cloud, restoring balance with a breathtaking burst of light and sound. It's nature's ultimate way of saying all things must seek equilibrium. So, as you tuck yourself in, remember the quiet, invisible dance of electrons and protons, the gentle tug-of-war that creates those surprising moments of static electricity. It's a testament to the universe's constant quest for balance, a reminder that even the smallest imbalances can create fascinating, fleeting phenomena all around us. And as we drift from these momentary sparks and sudden equalizations, perhaps tomorrow night, we can explore what happens when these tiny, restless charges don't just jump in a flash, but instead begin to flow in a steady, continuous stream, creating something we call current. Our exploration of electricity began with whispers of charge, of electrons held captive or gently coaxed to stay put, creating a silent tension in the air. We imagined them like tiny, sparkling dust motes, gathering on a balloon or clinging to a sweater after a cool, dry day. But now, as the night deepens and the world outside softens into dreams, let's imagine those charges are no longer content to simply linger. Imagine they stir, awaken, and begin a journey. This gentle awakening, this directed movement of countless tiny charges, is what we call electric current. It's the very heartbeat of modern life, though often unseen, a silent, tireless river flowing through the veins of our homes and cities. Think of it like a beautiful, clear river, once still and reflective in a quiet lake, now finding its path, a purpose, and beginning to flow towards the sea. The water, in our river analogy, is made of those incredibly numerous minuscule particles we call electrons, each carrying a tiny electrical charge, now encouraged to move in a coordinated dance. The rate at which these charges flow past a certain point, how swift and strong our electron river is measured in units called amperes, or amps for short. A single amp represents an incredible torrent of charges flowing every second, a testament to the immense activity happening invisibly all around us. But what stirs the river to flow? What gives it its gentle, persistent push? Just as a river needs a subtle slope, a difference in height to begin its journey, our electric current needs a kind of electrical push. We call this voltage, or potential difference. Imagine it as the gentle pressure that encourages our electrons to move from a place where they are more eager to leave to a place where they are more welcome to arrive, measured in tau volts. This unseen force is what a battery provides, or what comes from the wall outlets in your home. It's not the flow itself, but the energy or potential to create the flow. Think of a pump in a water system, tirelessly working to create the pressure that sends water through the pipes. The pump doesn't contain the water, but it provides the essential impetus for its movement. This voltage is the promise of movement, the potential energy waiting to be converted into the kinetic energy of flowing electrons. Now, for our electrons to embark on their journey, they need a path, a kind of riverbed. Some materials are like wide, smooth, welcoming canals for our electron river. These are called conductors. Metals, like the copper in the wires that weave through your walls, are excellent conductors. They have electrons that are not tightly bound to individual atoms, but are instead free to drift and move throughout the material, like eager dancers ready to join the flow. Silver, gold, and even humble aluminum are also wonderful conductors, each offering a slightly different quality to the electron river. In these materials, the electron path is relatively clear, allowing the current to flow with ease, much like a well-maintained road allows cars to travel smoothly. But not all materials are so welcoming. Some are like dense, impenetrable barriers, turning our electron river away completely. These are insulators. Rubber, plastic, glass, and even dry wood are common insulators. Their electrons are tightly held by their atoms, making it very difficult for them to break free and join the current. Imagine them as solid dams or thick, dense forests that the river simply cannot penetrate. This property of insulators is incredibly important for safety. It's why wires are wrapped in plastic, to keep the electron river flowing exactly where we want it, safely contained within its intended path, preventing it from straying into unwanted or dangerous areas. When we intentionally create a complete, unbroken path for our electric current to flow, we've made an electric circuit. It's a marvelous loop, a continuous journey for our electrons. A circuit must have a power source, like our battery or wall outlet, providing the voltage push, conductors, the wires, and a load, something that uses the electrical energy and converts it into another form, like a light bulb that glows, a motor that spins, or a speaker that hums a lullaby. Imagine our electron river flowing from the pump through a pipe, turning a small water wheel, our load, and then returning to the pump to begin its journey anew. It's a never-ending cycle, a closed loop that allows energy to be transferred and transformed. If there's any break in this loop, a switch is opened, a wire is cut, the river stops flowing. The circuit is open, and the dance of electrons ceases. As our electrons journey through the conductors, even the best riverbeds have some imperfections. There are tiny obstacles, atoms vibrating in their path, making it a little harder for them to move freely. This opposition to the flow of electric current is called resistance. Measured in ohms, resistance is like the friction in our pipes or the rocks and bends in our river that slow the water down. All materials offer some resistance, but some offer much more than others. A long, thin wire will have more resistance than a short, thick one, much like a long, narrow pipe will restrict water flow more than a short, wide one. The type of material also matters, as does its temperature. This resistance is not always a bad thing. In a light bulb, the filament is specifically designed to have high resistance, which causes it to heat up and glow brightly as electrons struggle to push through it. So we have the push of voltage, the flow of current, and the opposition of resistance, all working in concert within a circuit. More voltage means a greater push, potentially leading to more current. More resistance means a harder path, leading to less current for the same voltage. It's a delicate balance, an unseen negotiation, constantly happening within every electrical device around us. And what is the purpose of this tireless journey, this intricate dance of charges? It's to do work, to deliver power. When electrons overcome resistance in a load, they transfer their energy, converting it from electrical energy into other forms we can use: light, heat, sound, or motion. This rate at which electrical energy is converted or transferred is called electrical power, and it's measured in watts. Your nightlight might be just a few watts, gently converting electricity into a soft glow. A large refrigerator might use hundreds of watts, silently keeping your food cool. It's the ultimate outcome of the voltage-driven current pushing through resistance, the visible manifestation of electricity's quiet work. Circuits themselves can be arranged in different ways, each with its own special characteristics. Imagine a single-file line of tiny dancers, each needing to pass through a specific doorway before the next one can follow. This is like a series circuit. If one dancer stops or one doorway closes, the entire line comes to a halt. All the current flows through each component, one after another. If you've ever seen old Christmas lights where one bulb going out made the whole string dark, you've witnessed a series circuit in action. Then there are more parallel circuits. Picture our dancers having multiple doorways, multiple paths they can choose to take, all leading to the same destination. If one doorway closes, the other paths remain open, and the dance continues, though perhaps with fewer participants on that specific route. In your home, most electrical outlets and lights are wired in parallel. This means if one lamp burns out, the other lights in the room keep shining brightly, as their individual circuits remain complete. Each path in a parallel circuit receives the full voltage, but the total current from the source splits among the various paths. It's a clever way to ensure continuous operation and provide flexibility. Of course, with such powerful and invisible forces at play, safety is paramount. Just as we ensure our rivers have strong banks to contain their flow and gentle guardians to guide them, so too do our electrical systems. Insulation ensures the current stays within its wires, and clever devices like fuses and house circuit breakers act as gentle sentinels. If, for some reason, too much current tries to rush through a circuit, perhaps due to an accidental shortcut, these guardians will gently yet firmly open the circuit, stopping the flow before any harm can be done. They are the quiet protectors of our electrical world, ensuring the electrons always follow their safe, intended paths. As these tireless electrons continue their quiet journey, flowing through conductors, meeting resistance, and transforming their energy into light and warmth, we begin to appreciate the cleverness and precision of these unseen pathways. We've seen how they move, what drives them, and the paths they take. But what happens when these tiny travelers encounter even smaller, more intricate pathways? Pathways that can store and process information, allowing us to connect with distant whispers and explore new worlds within the realm of electronics. We'll drift into that fascinating story next. To understand how electrons navigate those pathways, we need to explore three fascinating aspects that work together like a silent, intricate dance, orchestrating all the wonders we witness. Imagine them as distinct personalities, each with a crucial role to play: voltage, resistance, and power. First, let's gentle our thoughts toward our voltage. Picture, if you will, a tranquil, shimmering lake held high up in the mountains, perhaps at the very top of a gentle, sloping peak. This lake isn't just any body of water. It represents the potential for movement, the stored energy ready to flow. The higher this lake sits, the greater its potential to push water downwards. In our world of electricity, this push is precisely what we call voltage. It's the electrical pressure, the electromotive force, a measure of the potential energy difference between 2 points in a circuit. Just like water won't flow unless there's a difference in height, electrons won't journey unless there's a voltage to gently nudge them along. We measure this subtle insistence in volts, a tribute to the pioneering Italian scientist Alessandro Volta. A higher voltage means a stronger, more insistent push, much like a taller waterfall holds more potential energy, ready to unleash a more powerful cascade. It's the quiet promise of energy, waiting to be unleashed, the difference in electrical potential that inspires electrons to leave their comfortable slumber and begin their incredible journey. Without this initial push, this potential difference, the electrons would remain still, and our lamps would stay dark, our devices silent. Voltage is the gentle invitation, the silent urging for movement to begin. Now, as our imagined water begins its descent from the elevated lake, it encounters a path. This path isn't always smooth and wide. Sometimes it's narrow. Sometimes it's lined with rough stones. Sometimes it's a winding, challenging route. This opposition to the flow is precisely what we call resistance. In the world of electricity, resistance is the measure of how much a material opposes the flow of electric current. Think of it as a gatekeeper, or perhaps a gentle friction, slowing down the diligent electron travelers. Some paths, made of materials like copper, are wide and smooth, offering very little resistance, allowing electrons to flow with ease. These are our excellent conductors. Other paths, perhaps made of glass or rubber, are like impassable walls, offering immense resistance, almost completely blocking the flow. These are our insulators, quietly ensuring our safety by keeping electricity contained. We measure this opposition in ohms, a name honoring Georg Ohm, who first defined this fundamental relationship. The longer a wire, or the thinner its diameter, the more resistance it offers, much like a longer, narrower pipe restricts water flow more than a short, wide one. Even temperature plays a role. For most materials, as they grow warmer, their resistance tends to increase as the atoms vibrate more vigorously, creating more bumps in the electron's path. Resistance isn't a villain, it's an essential element, allowing us to control and direct the electron's journey, ensuring they don't rush too fast or simply stop altogether. It shapes the path, guiding the flow, making sure the energy is delivered just right. So we have the push of voltage and the opposition of resistance. When these two meet, they determine the current, the actual flow of our tiny electron travelers. Current is the rate at which electric charge moves past a point in a circuit, like the steady stream of water flowing down our mountain path. It's the measurable motion, the actual river of electrons, and we gauge its strength in amperes, or amps for short, named after André-Marie Ampère. Georg Ohm, with his wonderful insight, discovered a beautiful relationship between these three. The stronger the voltage push, the greater the current. But the higher the resistance, the less current will flow. It's a delicate balance, expressed simply as Ohm's law. Voltage equals current multiplied by resistance, VOI-R. Imagine this. If our lake is very high voltage, a lot of water will want to flow. But if the path is very narrow and rocky, high resistance, only a little water will actually make it through, low current. Conversely, a gentle push, low voltage, down a wide, smooth path, low resistance, can still create a steady, gentle flow. This elegant interplay is at the heart of how every electrical device functions, a silent conversation between push, path, and flow. And what is the purpose of this push and this flow against resistance? It is to do work, to create an effect, to bring about change. This is where horsepower steps into our quiet story. Electrical power is the rate at which electrical energy is converted into another form of energy, such as light, heat, or motion. Think of it as the oomph, the actual work being accomplished by our flowing water. If our mountain stream is strong and flows quickly, it can spin a water wheel with great force, perhaps grinding grain or generating electricity. The speed at which that work is done, the actual brightness of a light bulb, or the warmth emanating from a toaster, that is power. We measure power in watts, named after the Scottish inventor James Watt, whose innovations in steam engines were foundational to understanding work and energy. A 60-watt light bulb uses 60 joules of electrical energy every second, transforming it mostly into light and a little heat. The power generated or consumed is directly related to both the voltage, the push, and the current, the flow. A higher voltage combined with a greater current will result in greater power, PXVI, meaning more work gets done, more light shines, or more heat is produced. It's the tangible outcome, the visible effect of the quiet dance between voltage and current. Sometimes, as our electrons bravely push their way through a resistant path, they bump and jostle against the atoms of the material. These tiny collisions generate friction, and just like rubbing your hands together creates warmth, these electrical bumps create heat. This phenomenon is known as Joule heating, named after James Prescott Joule, another brilliant mind who helped us understand energy. While sometimes seen as an inefficiency because energy isn't going directly into the desired work, like light or motion, it's also incredibly useful. It's the very principle that warms your electric blanket, heats the elements in your toaster, or makes an old incandescent light bulb glow, transforming electrical energy into comforting warmth and brilliant light. So, even the lost energy finds a purpose, a testament to the elegant efficiency of the universe, where energy is never truly destroyed, only transformed. So, as you rest your mind, picture this remarkable trio: the potential push of voltage, the moderating path of resistance, and the resulting work or effect of power. They are inextricably linked, each essential, each playing its part in the silent, tireless ballet that brings our modern world to life. From the tiny circuits in your phone to the mighty power lines stretching across landscapes, it is this fundamental understanding of how these three aspects interact that allows us to harness and utilize electricity. The silent conversation between the eager electrons, the guiding pathways, and the visible outcomes is a testament to the elegant order within the seemingly chaotic flow of energy. As we quietly reflect on this intricate dance, perhaps we can now appreciate the subtle forces that bring our everyday devices to life, even as they slumber beside us. Next, we might discover that these flowing electrons hold a beautiful secret, a connection to another invisible force that surrounds us all. Those tiny, industrious electrons journeying through our circuits hold a beautiful secret, a connection to another invisible force that surrounds us all: magnetism. Imagine, if you will, our bustling electrons, each one a tiny dancer, twirling and pirouetting through the wire. For the longest time, we thought electricity and magnetism were like two completely separate cosmic ballets, each dancing to its own tune. But then, a curious discovery was made, a moment that revealed they weren't just neighbors, but partners in an intricate, unseen waltz. It began with a simple observation. When an electric current, a steady stream of those dancing electrons, flows through a wire, something remarkable happens around that wire. It suddenly creates its own invisible magnetic field. Picture that wire, normally just a path for electrons, now gently enveloped in a soft, unseen magnetic aura, like a sleepy star surrounded by its own faint glow. This magnetic field, though invisible, is very real, capable of influencing nearby compasses, making their needles gently turn, just as a magnet does. It was like discovering that every time you played a tune, the air around you began to hum with a secret magnetic melody. This principle, that moving electric charges generate magnetic fields, is the very heart of what we call electromagnetism. It means that wherever electricity flows, a magnetic presence follows. And we've learned to harness this partnership in incredibly clever ways. Think of an electromagnet. It's one of the most elegant applications of this principle. Instead of just a straight wire with a faint magnetic field, imagine taking that wire and coiling it up, winding it around and around like a spiral staircase. Each turn of the wire is like another voice joining a choir, strengthening the magnetic field. And if you place a piece of iron, like a soft iron nail, inside that coil, it's as if you've given the choir a wonderful acoustic hall. The iron core amplifies the magnetic field, concentrating its power immensely. Now, with a simple flick of a switch, a powerful magnet springs to life, strong enough to lift heavy scrap metal or gently pull the clapper of a doorbell, creating that familiar chime. Turn the electricity off, and like a magician's trick, the magnetic field vanishes, leaving behind just an ordinary piece of iron. It's a temporary, controllable hug of magnetic force, there when you need it, gone when you don't. But the dance doesn't end there. Just as electricity can create magnetism, magnetism holds the power to create electricity. This is perhaps an even more astounding part of their secret handshake. Imagine you have our coiled wire again, but this time, there's no electricity flowing through it. It's quiet, dormant. Now, picture taking a permanent magnet, perhaps one of those cheerful refrigerator magnets, and moving it rapidly through the center of that coil, or even just waving it back and forth nearby. What happens? As the magnet glides past the wire, its invisible magnetic field brushes against the electrons within the wire, giving them a gentle nudge, a little push. And what does a push do to an electron in a conductor? It makes it move. It starts a current. Like a sleepy stream suddenly roused into a flowing river by a gust of wind, the electrons begin to journey. And we have created electricity from pure motion and magnetism. This magical phenomenon is called electromagnetic induction. It's crucial to remember that it's the change in the magnetic field that matters. If the magnet just sits still near the wire, nothing happens. It's like gently rocking a cradle. It's the back and forth, the movement that sets things in motion. This principle, discovered by the brilliant Michael Faraday, is the bedrock of how most of the world's electricity is generated. Think of the enormous generators in power stations. They are simply immense coils of wire spinning around powerful magnets, or powerful magnets spinning within coils of wire, constantly creating that elegant dance of changing magnetic fields to coax electrons into a flow. The rushing water of a waterfall or the powerful force of steam turns turbines which spin these magnets. And from that motion, light and life spring forth through the induced current. Now, let's add one more layer to this beautiful, intertwined story. What happens if you place a wire carrying an electric current within an existing magnetic field? Not just a wire creating its own field, but a wire entering the domain of another magnet's force. In this scenario, the magnetic field exerts a force on the moving electrons in the wire, causing the wire itself to move. Imagine a tiny, invisible hand reaching out from the magnet, giving the current-carrying wire a gentle push or pull. This is the very principle that makes electric motors spin. Electricity flows into a coil of wire, creating an electromagnet. This electromagnet then interacts with the magnetic field of a permanent magnet, or another electromagnet, and the resulting push and pull creates rotational motion. From the tiny motor in a toy car to the powerful engines in industrial machinery, it's all based on this magnificent dance of forces. Electricity makes magnetism, and magnetism exerts a force on electricity, turning invisible energies into tangible movement. So you see, electricity and magnetism are not separate entities, but two sides of the same wondrous coin, forever linked in a grand cosmic ballet we call electromagnetism. They are constantly creating each other, influencing each other, and through their intricate interplay, they power our world, carry our voices across vast distances, and even allow us to peer into the human body with technologies like MRI. It's a force so fundamental, so elegant, that it truly unifies much of what we perceive as energy and light. Wow. And speaking of light, this incredible electromagnetic partnership isn't just about wires and magnets. It's also about invisible waves that ripple through space, carrying energy without any physical connection. These are the electromagnetic waves, of which visible light is just one small, beautiful part. But that, my dear listeners, is a story for another peaceful moment, as we drift deeper into the wonders of our universe. This connection between electricity and magnetism reveals an even more enchanting secret, one where these two forces whisper to each other across the quiet void, each capable of awakening the other. Imagine, if you will, the world as a vast, intricate tapestry woven with threads of energy. We've seen how electricity flows, a river of tiny, diligent electrons, and how magnetism creates its own unseen pathways, a silent, pervasive presence. For a long time, these two phenomena were thought to be separate dances, each with its own rhythm. But then, a curious mind, much like a patient stargazer, began to notice a subtle interaction, a delicate exchange between them. This is the story of electromagnetic induction, a discovery that truly illuminated the interconnectedness of our universe. It tells us that not only can electricity create magnetism, as we explored with electromagnets and the graceful swirl around a current-carrying wire, but magnetism, in turn, can create electricity. It's like discovering that a melody played on one instrument can, under just the right conditions, awaken a resonant hum in another, previously silent one. But there's a crucial, tender nuance to this awakening. It's not just the presence of a magnetic field that coaxes electricity into being. Oh no, that would be too simple, too static. Imagine trying to lull a sleepy stream into flowing faster simply by placing a mountain beside it. The stream needs a nudge, a change in its surroundings to truly respond. And so it is with electromagnetic induction. The magic happens when there is change. Picture a serene, invisible magnetic field, a silent, shimmering pool of influence. Now, imagine a simple wire, a pathway for electrons lying dormant nearby. If that wire just sits there, perfectly still within the magnetic field, nothing happens. The electrons remain quietly in their places, like passengers gently resting in their seats. But what if we disturb that stillness? What if we move the wire through the magnetic field? Or, conversely, what if we keep the wire still and move the magnet? Suddenly, the electrons within the wire are stirred from their slumber. It's as if the moving magnetic field sweeps past them like a gentle wave, imparting a subtle push, a persuasive whisper that encourages them to flow. This movement, this interaction, creates an electric current. It's the change in the magnetic field that the wire experiences. The invisible magnetic lines of force being cut or crossed by the wire. That is the key. Think of it this way. The magnetic field is like a gentle, invisible river. If you place a small boat, our wire, perfectly still in the middle of a still river, it just floats. But if the river itself begins to flow, or if you gently pull your boat through the water, you feel the resistance, the push of the current against your hull. That push, for our tiny electrons, is the force that makes them drift collectively in one direction, forming an electric current. The faster you move the boat, the stronger that push feels, and the more vigorously the electrons are encouraged to flow. This is the essence of Faraday's profound insight. The magnitude of the induced electricity depends on the rate at which the magnetic influence changes. This principle, so simple yet so powerful, underlies countless wonders of our modern world. It is the very heart of the electric generator. Imagine a series of coils of wire arranged like a quiet labyrinth, nestled within a strong magnetic field. Now, with a gentle, continuous push, perhaps from the force of rushing water turning a turbine, or steam expanding, or wind coaxing giant blades to spin, these coils are made to rotate. As they spin, they are constantly sweeping through, and therefore cutting across, the invisible lines of the magnetic field. With every turn, every passing moment, the magnetic influence experienced by the wire coils changes, and this continuous change generates a continuous flow of electricity. It's a magnificent dance of mechanical motion, transforming into electrical energy, powering our homes and illuminating our nights with the quiet hum of distant generators. But the story deepens, for nature, in its infinite wisdom, often seeks a gentle balance. There's another layer to this induction, a subtle resistance, almost like a sigh, known as Lenz's law. It tells us that when a current is induced in a wire, that very current creates its own tiny magnetic field. And here's the clever part. This new magnetic field always tries to oppose the change that caused it. If you try to push a magnet into a coil, the induced current will create a magnetic field that pushes back, ever so slightly, resisting your motion. If you try to pull it out, the induced current will try to pull it back in. It's nature's way of ensuring that energy is conserved, a gentle reminder that every action has an equal and opposite reaction, even in the invisible realms of electricity and magnetism. This dance of opposing forces is not a hindrance. It's an elegant mechanism that allows for even more fascinating applications. Consider the transformer, a seemingly simple device with no moving parts, yet indispensable for our electrical grids. Inside, you'll find two coils of wire, not touching, but wrapped around a shared iron core. When an alternating current, a current that constantly changes direction and strength, flows through the first coil, it creates a constantly changing magnetic field within the iron core. This changing magnetic field then induces an alternating current in the second coil. By carefully choosing the number of turns in each coil, we can step up or step down the voltage of the electricity, efficiently transmitting power over vast distances without losing too much energy. It's like a silent interpreter, adjusting the intensity of the electrical message for its long journey or its final destination. And what about the quiet convenience of induction cooktops? Beneath the smooth, cool surface, coils create a rapidly changing magnetic field. When you place a compatible pot or pan on top, this changing field induces swirling currents, called eddy currents, directly within the metal of the cookware itself. These eddy currents encounter resistance, generating heat within the pot, not on the surface of the stove. It's a wonderfully efficient and safe way to cook. A gentle, invisible warmth transferred directly to where it's needed most. Or the familiar comfort of wireless charging, where a changing magnetic field from a pad induces a current in a coil within your device, quietly replenishing its energy without a single cable. From the immense power of hydroelectric dams to the subtle glow of a wirelessly charged phone, electromagnetic induction is a constant, quiet performer, orchestrating the conversion and transfer of energy all around us. It's a testament to the profound interconnectedness of the universe, a lullaby whispered between magnetic fields and electric currents, ensuring that energy, in its many forms, is never truly lost, but merely transformed, ready to serve us in new and ingenious ways. As we reflect on this gentle whisper of induction, a question naturally arises. Where does all this electricity we've been exploring truly come from? How do we it into existence? A fascinating question often whispers through the mind, where does all this invisible energy truly come from? How do we coax it into existence, inviting those countless tiny electrons to begin their tireless dance through our wires? Imagine, if you will, that electricity is a magnificent shy river, constantly flowing, but often hidden beneath the surface of the world. Our task, as humans, is to build clever mechanisms to dip our cups into this river, to gently guide its currents, and transform its energy into the particular flow that lights our lamps and powers our devices. It's a captivating challenge, a blend of ancient wisdom and modern ingenuity, where the fundamental principle often remains wonderfully simple: to get things to spin. Indeed, at the heart of most electricity generation lies a remarkable invention known as the generator. Picture it as a silent, invisible ballet between magnets and coils of wire. When a magnet spins near a coil, or a coil spins within a magnetic field, something magical happens. The magnetic field, invisible yet powerful, nudges the electrons within the wire, compelling them to move, to flow. This gentle nudge is called electromagnetic induction, and it's the spark that ignites the river of electricity. So, our primary goal across most methods is simply to find a way to make something spin a turbine, which then turns the generator. Let's begin our journey through these power-producing landscapes. For a very long time, and still significantly today, humanity has relied on the Earth's deep, ancient memories, the stored sunlight of millions of years, locked away in what we call fossil fuels. Think of vast libraries of energy carefully pressed and preserved over eons. When we speak of coal, natural gas, or oil, we're tapping into this ancient warmth. In these power plants, we carefully burn these fuels, releasing their stored energy as heat. This heat is then used to boil water, creating immense clouds of superheated steam. Imagine a giant, powerful teapot. This steam, eager to expand, rushes through a series of fan-like blades, a turbine. The force of the steam pushes these blades, making the turbine spin with incredible speed and power. And guess what the spinning turbine is connected to? Yes, our trusty generator, which then performs its silent dance, turning that mechanical spin into the flow of electrons, sending electricity humming through the grid. A slightly different, yet equally powerful approach to harnessing heat comes from the very heart of matter itself: nuclear power. Here, we don't burn fuels in the traditional sense. Instead, we carefully split the nuclei of heavy atoms, a process called fission. This delicate dance of atomic particles releases a tremendous amount of heat, far more concentrated than burning fossil fuels. This intense heat, again, is used to boil water, creating high-pressure steam that drives those magnificent turbines, which in turn spin the generators. It's like gently coaxing a tiny, powerful sun to warm our world, but within the meticulously controlled confines of a power plant where every step is monitored with incredible precision. But what if we don't need to create heat at all? What if nature provides the spinning force directly? Let's turn our gaze to the majestic flow of water. Hydropower is one of the oldest and most elegant ways we've captured electricity. Imagine a vast, deep lake held back by an imposing dam. At the base of this dam, large pipes, like silent tunnels, allow a controlled rush of water to plunge downwards. The sheer weight and force of this falling water are immense, and as it cascades, it crashes against specially designed turbines, causing them to spin with tremendous force. Again, that mechanical spin is deftly captured by the generator, transforming the river's might into electrical power. It's as if the earth itself is running a giant, tireless treadmill, with the water providing the endless energy for the spin. Now, let's look to the skies, to the invisible currents of the wind. Wind power has become an iconic symbol of modern energy generation. Think of those towering, graceful wind turbines, their elegant blades slowly sweeping across the horizon like silent sentinels. Each blade is designed like an airplane wing, skillfully catching the kinetic energy of the moving air. As the wind pushes against them, the massive blades begin to turn, spinning a shaft that leads to, you guessed it, a generator. Even a gentle breeze can coax these giants into motion, transforming the wind's whisper into a powerful electrical current. It's a dance with the very breath of the planet. And what about the most ancient, powerful source of energy of all? The sun itself. Solar power offers a unique and direct pathway to electricity. Unlike the spinning turbines we've discussed, solar panels work in a fundamentally different way. They are made of special materials called semiconductors, often silicon, arranged in what we call photovoltaic cells. When sunlight, which is made of tiny packets of energy called photons, strikes these cells, it's like a gentle tap on a drum. These photons are absorbed by the semiconductor material, giving the electrons within it just enough energy to break free and start moving. This directed flow of electrons is, by definition, an electric current. So a solar panel doesn't need a generator. It directly converts sunlight into electricity. It's like tiny electronic gardeners, tending to photons and guiding their energy directly into our homes. A silent whisper from the sky transformed into light and warmth. Beyond these main methods, there are other clever ways we invite electrons to dance. Geothermal power, for instance, taps into the Earth's internal heat, drawing steam or hot water from deep underground to spin turbines. It's like harnessing the planet's own warm embrace. And biomass, which uses organic materials like plants or waste, can be burned to create steam, or even decomposed to produce gases that power engines, offering a way to turn nature's recycling into useful energy. So you see, whether it's the ancient warmth of the earth, the relentless rush of water, the invisible push of the wind, or the direct embrace of the sun, all these magnificent methods share a common purpose: to gather energy in its various forms and gently guide it into the familiar, usable flow of electricity. Each method is a unique story, a different kind of cleverness applied to the fundamental task of awakening those tiny electrons. And once they are awakened, once that river of electricity begins to flow, it must travel vast distances to reach us. How does it make that incredible journey? Our generated electricity must travel incredible distances through a system far grander and more intricate than we might imagine, the magnificent dance of the electrical power grid. Imagine, if you will, a vast, invisible tapestry woven across continents, a silent, pulsating web of energy that never truly sleeps. It's the circulatory system of our modern world, carrying the lifeblood of power to every corner, every device, every quiet light in a sleeping window. Think for a moment about all the energy we use, even as we lie here, tucked away. Where does it all come from? The grid is its birthplace, its highway, and its delicate delivery system, all rolled into one. Far away, perhaps by a roaring waterfall, where the sheer force of descending water spins enormous turbines, or in the heart of a vast wind farm, where giant, graceful propellers catch the invisible currents of the air, or under the warmth of the sun, where countless shimmering panels gather light. These are the gentle birthplaces of our electricity. We might also find it in the quiet hum of a power station, where controlled heat from fossil fuels or the harnessed power of atoms turns water into steam, sending other turbines into a powerful rhythmic spin. Each of these places transforms one kind of energy, kinetic, solar, chemical, or nuclear, into the electrical energy that we need. Once this energy is born, it begins its incredible journey. But to travel across vast landscapes over mountains and valleys, it needs a special kind of help. Imagine trying to push water through a very long, narrow hose. You'd lose a lot of its force along the way, wouldn't you? Electricity faces a similar challenge. If we sent it at the pressure it's born at, much of its precious spark would be lost, turning into warmth, dissipated into the air along the way, a phenomenon known as resistive loss. To overcome this, the grid employs a clever trick. It steps up the voltage, the electrical pressure, to incredibly high levels. At special substations, enormous humming transformers, the quiet giants of the grid, take the newly generated electricity and boost its voltage significantly, sometimes hundreds of thousands of volts. This is like turning a gentle stream into a roaring, high-speed river ready for its long journey. These rivers of high-voltage electricity then flow along the main arteries of the grid, the towering transmission lines, strung high between the familiar, majestic pylons you might see stretching across the countryside. These silvery giants, with their outstretched arms, are the silent custodians of our power, carrying the energy at high speeds, minimizing those wasteful losses. For this long-distance journey, we primarily use alternating current, or AC. This kind of current, which gently switches its direction many times a second, typically 50 or 60 times a second, depending on where you are in the world, is particularly well suited for high-voltage transmission, precisely because it's so easy to step up and step down using those clever transformers. It's like a flexible dancer, easily adjusting its movements for the journey ahead. But a high-speed river is too powerful for our homes and businesses. It needs to be tamed, slowed down, made safe for everyday use. So, as the electricity approaches our towns and cities, it encounters more substations, more transformers. Here, the process is reversed. The voltage is stepped down from those incredibly high transmission levels to much lower, more manageable levels. Imagine our roaring river now branching into smaller, gentler streams, and then into countless delicate rivulets. These lower voltage lines form the distribution network, the intricate web of poles and wires that you see lining our streets, whispering through our neighborhoods. These are the final, tender whispers of power, ready to flow into our homes, illuminating our bedside lamps and charging our devices as we sleep. Plan. The true marvel of the power grid, however, lies not just in its vastness, but in its profound intelligence and continuous ballet of balance. Every single part of this enormous, interconnected system must operate in perfect harmony, synchronized to the exact same frequency, that rhythmic switching of the alternating current. If one part of the grid falls out of sync, even slightly, it can cause disruptions, like a single discordant note in a grand symphony. Imagine a colossal, invisible orchestra where millions of tiny instruments must play precisely together, responding instantly to the baton of an unseen conductor. This synchronization is monitored and maintained with breathtaking precision, moment by moment. And then there's the delicate seesaw of supply and demand, known as load balancing. At any given second, the amount of electricity being generated must precisely match the amount being consumed. If too much power is generated, the system can become unstable. If too little, the lights flicker and can go out. This balance is constantly shifting. As we wake up in the morning, more lights come on, more kettles boil, more machines whir. Demand rises. As we go to sleep, demand gently falls. Control centers, often humming quietly in unassuming buildings, are the watchful guardians, the silent conductors of this immense orchestra. Skilled engineers monitor countless data points, adjusting generation, redirecting power, and anticipating needs, ensuring that the grand seesaw remains perfectly level, even as the world changes its rhythm throughout the day and night. In the quiet of the night, as we rest, this vast network hums on, an unseen servant, tireless and constant. It's a testament to human ingenuity, a colossal feat of engineering that powers our dreams and fuels our tomorrow. And as we drift deeper into the wonders of this invisible force, there's another fascinating aspect of electricity that touches our lives directly, something we interact with every day in countless ways. But that, my friends, is a tale for a moment further along our journey into the luminous world of electricity. As the day gently fades into night, we find ourselves surrounded by the quiet hum and subtle glow of electricity's everyday miracles. It's not just a grand abstract force, but a tireless, invisible helper, weaving its way through the very fabric of our homes, bringing comfort and connection to our every moment. Tonight, let us quietly explore the everyday magic it performs, the wondrous tasks it accomplishes while we sleep, or simply enjoy a quiet evening. Imagine first the soft light that might be illuminating your room right now. Once, before electricity became our constant companion, such light would have been a flickering candle flame or a dim oil lamp. But now, with a simple flick of a switch, a tiny sun awakens. In our traditional light bulbs, those little glass spheres, a very special fine wire, often made of a strong metal like tungsten, receives a rush of these energetic little electrons. As they journey through this thin pathway, it's like a bustling crowd trying to squeeze through a narrow gate. They bump and jostle, creating a gentle friction, and this friction, this resistance, causes the wire to grow incredibly hot, so hot it begins to glow brightly, emitting that warm, familiar light. It's a beautiful transformation, isn't it? Electrical energy patiently turning into light and a little warmth. And then we have the newer, more efficient stars of our homes, LED lights. These are truly fascinating. Instead of making a wire hot to glow, LEDs use special materials called semiconductors. Imagine these materials as tiny, organized dance floors where electrons can gracefully leap from one energy level to another. When our electrical current flows through them, these electrons perform their energetic leaps, and with each successful jump, they release a tiny packet of light, a photon, almost like a microscopic sigh of illumination. Billions upon billions of these tiny sighs combine to create the brilliant clear light we see. They are incredibly clever, these LEDs, turning almost all their electrical energy directly into light, with very little wasted as heat. They are like efficient, silent messengers, bringing light without much fuss. Now, let's turn our thoughts to warmth. Perhaps on a chilly morning, you've snuggled into a warm bed or enjoyed a comforting cup of tea. Electricity is often the unseen artisan behind this warmth. Think of your toaster, patiently turning bread into golden brown perfection, or a kettle, serenely bringing water to a boil. These devices use special heating elements, often coiled wires made of a material called nichrome. Just like our light bulb filament, these wires have a much higher resistance to the flow of electrons. It's like sending our busy electrical currents down a particularly bumpy and winding road. The more resistance they encounter, the more they struggle, and the more energy they expend, turning that electrical energy almost entirely into heat. This is a scientific principle known as Joule heating, where the electric current pushed through resistance literally creates warmth. So the next time your warm blanket or a hot drink comforts you, remember the tireless work of those electric currents, patiently creating warmth just for you. But electricity isn't just about light and heat. It's also about movement, about bringing things to life. Think of a whirring fan on a warm day, a washing machine gently tumbling your clothes, or a vacuum cleaner humming as it cleans. These devices rely on the magic of electromagnetism to create motion. Deep within them, you'll find what we call an electric motor. Here, the flowing electricity isn't just creating heat, it's creating invisible forces. When electric current travels through a coil of wire, it creates a temporary magnetic field, much like a fleeting, invisible hand reaching out. This temporary magnetism then interacts with other permanent magnets or other coils, pushing and pulling them in a precise rhythmic dance. It's this constant pushing and pulling, this delicate yet powerful interplay of magnetic forces that causes the motor to spin, turning electrical energy into mechanical energy, into the very motion that makes our appliances work. It's like tiny, unseen dancers constantly twirling, bringing life and activity to our homes. Class Sun. Then there are the silent communicators, the weavers of information, our phones, computers, and televisions. These are perhaps the most intricate and dazzling applications of electricity. They don't just use current to glow or spin, they use it to think, to store memories, and to paint vibrant pictures. Here, the electricity is guided through incredibly complex pathways etched onto tiny chips, made from materials like silicon. These are our semiconductors again. Within these chips are billions of microscopic switches called transistors. Each transistor is like a tiny gatekeeper, able to quickly turn the flow of electricity on or off. By rapidly switching these tiny gates, electricity can represent information, like a secret code of on and off, which computers interpret as zeros and ones. This binary language allows them to process vast amounts of data, display intricate images, play beautiful sounds, and connect us to worlds beyond our own. It's a breathtaking ballet of electrons, orchestrated to create stories, knowledge, and connection, transforming electrical signals into light and sound and boundless information. And where would we be without the ability to hold on to this precious electricity? Our phones, our laptops, even electric cars rely on batteries. These clever devices don't generate electricity from thin air. Instead, they are like tiny, silent reservoirs. Inside, chemical reactions patiently store up energy. When we need power, these reactions are gently reversed, releasing a steady stream of direct current, those same energetic electrons, to power our portable devices. And when they run low, we simply plug them in, and our wall outlet, providing alternating current, gently coaxes the chemical reactions to reverse once more, refilling our reservoirs for another day. Of course, with such a powerful and versatile helper, it's also important to remember the vigilant guardians that keep us safe. Electricity, while wonderful, can also be mischievous if not handled with respect. That's why every home has silent protectors like fuses and circuit breakers. Imagine our electrical currents as a river. Sometimes, due to a problem with an appliance or too many devices trying to draw power at once, the river swells into a dangerous flood. A fuse is like a tiny sacrificial bridge in that river. If the current becomes too strong, the bridge melts, instantly breaking the circuit and stopping the dangerous flow, protecting your home. Circuit breakers do a similar job, but are like sturdy, resettable gates. When the current becomes too overwhelming, the gate automatically swings shut, stopping the flow. Once the problem is fixed, you can simply reset the gate. These guardians are constantly watching, ensuring that our invisible helper remains a friend, not a foe. So, as you drift deeper into slumber, take a moment to appreciate this quiet, profound presence around you. From the gentle glow of a nightlight to the silent hum of a refrigerator, electricity is a constant, faithful servant, turning unseen energy into light, warmth, motion, and information, making our world a more comfortable, connected, and truly wondrous place. It's a testament to the ingenuity of both nature and human curiosity. As these thoughts begin to settle, and perhaps we should also consider the moments when this powerful helper needs our respect and understanding, when we must be mindful of its boundaries. Now, as we've journeyed through the incredible world of electricity, admiring its power and its gentle service, it's natural to also consider its more formidable side. Like a mighty river that provides us with energy and nourishes the land, electricity, too, demands respect and understanding of its boundaries. It's not a force to be feared, but one to be understood with care, especially when it comes to the rare instances where its powerful current might stray from its intended path. And imagine, for a moment, that electricity is like a spirited, invisible river flowing through hidden channels within our homes. Most of the time, this river stays perfectly within its banks, guided by the wires, powering our lights and devices with a comforting hum. But what happens when, just occasionally, this powerful current finds an unexpected detour, or when its banks are not quite strong enough to hold its energy? One of the most important concepts to gently understand is what we call an electric shock. This occurs when the human body, or even an animal's body, inadvertently becomes part of the electrical circuit. Our bodies, you see, are made mostly of water and salts, which makes us rather good conductors of electricity. When a live electrical component is touched, and there's another path for the current to flow, often through the body to the ground, then the current takes that path through us. It's like our body accidentally becomes a bridge for the electrical river to cross. When this happens, the effects can range from a tingling sensation to something far more serious. The current, which is the flow of those tiny electrons passing through our tissues, can cause our muscles to involuntarily contract. This is why sometimes a person who touches a live wire might find themselves unable to let go, their muscles clenching in response to the electrical signal. More critically, if enough current passes through the chest, it can disrupt the delicate electrical rhythm that keeps our heart beating steadily. Our heart is a marvel of biological electricity with its own internal pacemaker, and a sudden external jolt can confuse and override these natural signals, leading to a condition called ventricular fibrillation, where the heart quivers ineffectively instead of pumping blood. Additionally, the very flow of current through the body generates heat, much like how a wire gets warm when electricity passes through it, and this can lead to severe burns, both on the skin and internally, along the path the current took. The severity of the shock depends on several factors: the voltage, which is the push behind the current, the amount of current that flows, the resistance of the body. Dry skin, for example, offers more resistance than wet skin. The path the current takes through the body, a path through the heart is far more dangerous, and the duration of the contact. It's a complex interplay, but the underlying scientific fact is simply the passage of current through conductive living tissue. Sometimes, the electrical river finds an unintended shortcut, not necessarily through a person, but within the wiring itself. This is what we call a short circuit. Imagine our electrical river flowing along its carefully constructed path, perhaps through a lamp. But suddenly, two bare wires carrying different potentials touch each other, perhaps because their protective insulation has worn away. It's like the river suddenly finds a very steep, very direct, and very wide waterfall straight to a lower level, bypassing all the intricate machinery it was supposed to power. This new, unplanned path offers very little electrical resistance. Because resistance is low, a huge amount of current rushes through this shortcut, much more than the wires are designed to carry. This sudden surge of current causes a rapid and dramatic increase in heat. You might see sparks, or even a sudden flash of light, and the wires can quickly become incredibly hot, hot enough to melt plastic insulation and even start a fire. It's a runaway situation, and it's one of the most common causes of electrical fires. Closely related to this idea of too much current is an overload. Picture that same electrical river, but this time, instead of taking a shortcut, we've simply asked too much of it. We've plugged in too many appliances into one circuit: a toaster, a microwave, a coffee maker, perhaps a hair dryer, all demanding their share of the electrical flow from the same set of wires. Each appliance draws a certain amount of current, and if the total demand from all these devices exceeds the safe carrying capacity of the wires in that circuit, then those wires begin to heat up, just like during a short circuit, but perhaps more slowly. They become like a highway with far too many cars, getting congested and hot. This sustained overcurrent leads to excessive heat generation, which can melt the wire's insulation, again creating a serious fire hazard. It's a silent stress, building up until it becomes dangerous. But fear not, for our clever engineers and scientists have designed brilliant guardians to protect us from these potential stray currents and overwhelming demands. The first line of defense is Insulation. Think of insulation as the sturdy, protective skin that encases our electrical wires. It's made of materials like plastic or rubber, which are excellent electrical insulators, meaning they have very high electrical resistance and strongly resist the flow of current. They keep the electrical river safely contained within its banks, preventing it from touching anything it shouldn't. Without good insulation, our homes would be a maze of dangerous, exposed currents. Another crucial guardian is grounding, sometimes called earthing. Imagine that every electrical appliance with a metal casing has an emergency escape route, a dedicated safety wire that connects directly to the earth itself. If, due to a fault, a live wire inside the appliance accidentally touches its metal casing, the current would then flow through this safety wire directly into the ground, instead of waiting for a human hand to touch the casing and provide a path. This grounding wire provides a very low resistance path for fault currents, quickly dissipating the dangerous electricity and preventing the appliance's exterior from becoming live and hazardous. It's an invisible but vital safety net. And then we have the ultimate sentinels, the watchful gatekeepers of our electrical circuits. Fuses and circuit breakers. These devices are specifically designed to be the weakest link in a circuit, but in a good way. If there's a short circuit or an overload, if that electrical river suddenly tries to rush too fast or demands too much from its banks, the fuse or breaker will intentionally break the circuit. A fuse contains a thin wire that melts and breaks when the current exceeds a safe limit, while a circuit breaker is a switch that automatically trips open under the same conditions. Both achieve the same goal. They interrupt the flow of electricity before the wires can overheat to a dangerous level, thus preventing fires and protecting our homes. They are the heroes that sacrifice themselves or stand guard, silently waiting to leap into action when danger threatens, keeping the electrical river in check. We also need to remember a very important fact about electricity and, water. Pure water, surprisingly, is a poor conductor. But the water that flows from our taps and the water in our bodies is full of dissolved minerals and impurities, and these make it a very good conductor indeed. Water essentially opens up a superhighway for electricity. That's why it's incredibly dangerous to use electrical appliances near bathtubs, sinks, or in wet environments. A tiny splash, a damp hand, can drastically lower the body's resistance and create a very easy path for a dangerous current to flow, turning what would have been a mild shock into a severe, life-threatening one. Water makes the boundaries of our electrical river much wider and less predictable. Finally, a word about the simple effects of time and wear, damaged cords and appliances. Over time, the insulation on cords can become frayed or cracked, perhaps from being bent too often or chewed by a curious pet. This exposes the live wires beneath. An appliance might also suffer internal damage, perhaps from a drop, leading to internal wiring becoming loose or exposed. These damaged areas are like tiny breaches in the protective banks of our electrical river, creating vulnerabilities where the current can escape and cause a shock or a short circuit. It's a quiet reminder to always inspect our electrical tools and devices to ensure their protective shields are intact. So, While electricity is an amazing helper in our lives, bringing light and comfort and making our world buzz with activity, it's also a powerful force that requires our understanding and respect. By appreciating the science behind electrical hazards, understanding current's path, the dangers of overloads and short circuits, and the brilliant simplicity of insulation, grounding, fuses, and circuit breakers, we can live safely and harmoniously with this incredible energy. It's about being aware, not afraid. And as we've explored these unseen protections that keep us safe, you might wonder, how exactly are these clever guardians, these watchful sentinels, built into the very fabric of our homes and cities? How do we ensure that every electrical journey, from the power plant to your bedside lamp, is a safe and gentle one? Let's drift a little deeper into that thought, as we consider the larger network that brings electricity to life safely and reliably. The hum of our devices, the glow of our lamps, the warmth in our homes, all powered by a marvel we often take for granted: electricity. It's a tireless, invisible servant, weaving its way through wires and circuits to bring our modern world to life. But for all its power, electricity has a curious secret, a subtle fragility. It's incredibly difficult to hold on to. Think of it like a beautiful fleeting melody, played precisely when it's needed, but vanishing the moment the performance ends. This instantaneous nature has always been a fundamental challenge, especially as we dream of a future powered entirely by the sun's gentle warmth and the wind's steady breath, energies that don't always align with our demand. While lithium-ion batteries have transformed our portable devices and electric vehicles, their scale, cost, and lifespan for truly grid-level storage demand a new generation of solutions, a symphony of diverse innovations. Imagine, if you will, the journey into this future. Our first destination takes us deeper into the very heart of the battery, reimagining its inner workings. Here, scientists are diligently crafting what are known as solid-state batteries. Picture a conventional lithium-ion battery as a tiny, bustling city where charged particles, like energetic messengers, zip through a liquid electrolyte, a kind of busy, watery highway. While efficient, this liquid can sometimes be a source of safety concerns, and it limits how densely we can pack the energy. In a solid-state battery, this watery highway is replaced by a rigid, unyielding, solid material. It's like transforming a winding river into a sturdy, unwavering bridge. This change promises not only significantly higher energy density, meaning more power in a smaller, lighter package, but also enhanced safety, eliminating the risk of flammable liquid electrolytes. It's a leap towards batteries that could power longer-range electric planes or truly revolutionize grid storage with unparalleled reliability, lasting for decades rather than years. But what if the very scarcity of lithium itself poses a challenge? Our gaze then turns to a far more abundant element, one that dances in every ocean wave and sits in every grain of common salt: sodium. Enter the realm of sodium-ion batteries. While lithium-ion batteries are like finely tuned racing cars, sodium-ion batteries are evolving into sturdy, reliable workhorses. Sodium is plentiful and cheap, making these batteries far more democratic, accessible to every corner of the globe. Their energy density might be slightly lower than their lithium cousins for now, but ongoing research is rapidly closing that gap. Their inherent low cost, excellent safety profile and robust performance make them ideal candidates for stationary grid storage, where space might not be as critical as the sheer volume of stored energy and the cost-effectiveness of the solution. They could become the silent guardians of our renewable energy grids, absorbing excess solar power by day and releasing it steadily through the night. A constant, gentle pulse drawn from the very essence of the sea. Our exploration continues, leading us to a truly unique approach to energy storage. Flow batteries. Unlike traditional batteries that store energy within a single sealed unit, flow batteries separate the energy storing chemicals into two external tanks. Imagine two vast reservoirs, one holding a positively charged liquid electrolyte, the other a negatively charged one. When electricity is needed, these liquids are gently pumped through a central reactor, where an electrochemical reaction occurs, generating power. When excess electricity is available, the process is reversed, recharging the liquids. The sheer brilliance of this design is its scalability. Want more energy capacity? Simply build bigger tanks. The beauty of flow batteries, particularly those like vanadium redox flow batteries, lies in their remarkable durability. They can be charged and discharged countless times without degradation, retaining their full capacity over decades. This makes them perfectly suited for the long-duration, high-cycle demands of grid-scale energy storage, acting like an endless, patient river, always flowing, always ready to lend its strength without ever tiring. And what if we could simply breathe in our energy? This brings us to the fascinating potential of zinc-air batteries. These batteries quite literally draw oxygen from the surrounding air to drive their electrochemical reactions. Imagine a technology that uses one of the most abundant elements on Earth, oxygen, and pairs it with another relatively inexpensive metal, zinc. The theoretical energy density of zinc-air batteries is remarkably high, meaning they could store a lot of power for their weight. However, the challenge lies in their rechargeability and lifespan. Coaxing them to consistently and reliably inhale and exhale energy over thousands of cycles is an ongoing scientific quest. Yet, the allure of such an inherently inexpensive and abundant material source keeps researchers relentlessly pursuing its perfection, dreaming of a battery that could literally breathe life into our energy needs. But the future of storage isn't just about chemical reactions. It also harnesses the elegant simplicity of physics. Consider compressed air energy storage, or CAES. Here, excess electricity isn't converted into chemical bonds but into physical pressure. Picture vast underground caverns, perhaps disused salt mines or rock formations. When renewable energy overflows, powerful compressors pump air into these geological lungs, squeezing it under immense pressure. Then, when the grid demands power, this compressed air is released, rushing upwards to spin turbines and generate electricity. It's like the Earth itself takes a deep, silent breath, holding it until needed, then exhaling a powerful gust of energy. These systems are already operational, demonstrating the potential for massive, long-duration energy storage, making them critical for balancing large renewable energy inputs. And speaking of elegance, what about the oldest force we know, gravity? This leads us to gravity-based storage systems. Envision tall modular towers where heavy composite blocks, perhaps made from recycled materials, are meticulously lifted to great heights using electric cranes when there's an abundance of renewable energy. Each lifted block stores a silent reservoir of potential energy. When the grid requires power, these blocks are then gently lowered, and the controlled descent spins generators, converting that potential energy back into electricity. It's like building vast, silent libraries of stored power, where the force that keeps our feet on the ground is precisely harnessed to keep our lights on. Companies are already deploying these innovative systems, showcasing a beautifully straightforward and infinitely scalable way to store energy without complex chemicals or geological requirements, relying purely on the timeless power of weight and height. Sometimes, the simplest approach is to embrace the warmth. This brings us to thermal energy storage. Here, excess electricity is used to heat large volumes of material like molten salt or specially designed sand to extremely high temperatures. These materials act like a giant, perfectly insulated thermos, holding on to that heat for hours or even days. When electricity is needed, the stored heat is then used to boil water, creating steam that drives conventional turbines to generate power, much like a traditional power plant, but fueled by the sun's captured warmth or the wind's gentle power. It's akin to baking a magnificent loaf of bread and then slowly slicing it as needed, releasing its stored warmth and sustenance over time. This method is particularly promising for large-scale, long-duration storage, especially when paired with concentrated solar power plants, where the sun's energy is directly focused to create heat. Finally, we encounter a fascinating shapeshifter in the energy world: hydrogen. While not strictly a battery in the traditional sense, green hydrogen represents a powerful form of energy storage and an incredibly versatile energy carrier. When renewable electricity is abundant, it can be used to split water molecules into hydrogen and oxygen through a process called electrolysis. This green hydrogen can then be stored as a gas or even liquefied, ready for deployment. When power is needed, this hydrogen can be fed into fuel cells to generate electricity directly, or even combusted in turbines, much like natural gas, but without the carbon emissions. It's like transforming fleeting electrical energy into a concentrated, transportable essence that can then be turned back into power or used to fuel heavy industries, ships, or even airplanes. An invisible, potent messenger carrying renewable energy across vast distances and through time. The future of electricity storage, dear listeners, is not a singular path, but a grand tapestry woven from many threads of innovation. It's an orchestra where solid-state batteries provide the swift, intense solos for devices and vehicles, sodium-ion and flow batteries offer the steady, deep rhythm for our grids, mechanical systems provide the robust, long-term foundations, thermal storage adds a comforting, enduring warmth, and hydrogen acts as the versatile grand maestro, conducting energy across time and space. Each technology has its unique strengths, its perfect niche, and together they are being developed to create a resilient, sustainable energy ecosystem that can truly capture and hold the fleeting power of nature. As we ponder these intricate designs and grand visions, our minds can wander, much like the gentle currents of these future energy flows. In our next session, we'll turn our attention to another fascinating aspect of our energy landscape, exploring as the world outside drifts into a peaceful slumber. A quiet revolution is stirring beneath the surface, shaping how we'll live with electricity in the years to come. It's a gentle evolution, guided by curious minds and innovative spirits, all working to make our dance with electrons even more harmonious and sustainable. Imagine, if you will, a world where our energy feels lighter, freer, more attuned to the rhythms of nature. Much of this new dawn begins with how we store electricity. For so long we've relied on our trusty batteries, these quiet little reservoirs that hold energy until we need it. But like any good story, there's always a next chapter, and for batteries, that chapter is unfolding with fascinating new designs. Consider the concept of solid-state batteries. Up until now, many batteries have used a liquid or gel-like substance, an electrolyte, to allow charged particles to move from one side to the other. Think of it like a bustling river flowing between two banks. But what if that river could become a solid, stable pathway? Solid-state batteries replace this gooey liquid with a solid material, creating tiny, solid fortresses of energy. This seemingly small change brings with it a cascade of benefits. These new batteries promise to be safer, less prone to overheating, and potentially able to hold far more energy in a smaller space. Imagine your phone lasting days on a single charge, or an electric car traveling vast distances, all thanks to these silent, steadfast pools of energy that are both incredibly powerful and wonderfully robust. They're like miniature, unshakable mountains, holding vast reserves of power within their very structure, ready to release it smoothly and safely when called upon. Then there are the majestic flow batteries. Unlike their solid-state cousins that keep all their chemistry contained within a single unit, flow batteries separate their energy-storing liquids into large, external tanks. Think of it as two separate rivers, flowing in their own paths, exchanging their energy secrets only when needed. When you want to generate electricity, these two liquid electrolytes are pumped into a central cell where they react, releasing electrons. When you want to recharge, the process is reversed. This unique design means you can scale the power, how fast you deliver electricity, independently from the energy capacity, how much electricity you can store, simply by changing the size of the tanks. This makes them exceptionally well suited for large-scale grid storage. Imagining storing vast quantities of solar or wind energy for an entire town, releasing it steadily even when the sun has set or the wind has died down. They are like deep, patient wells, capable of holding immense amounts of energy for very long periods, patiently awaiting their moment to nourish our homes and cities. Beyond storage, another exciting whisper on the electrical breeze is wireless power transfer. Can you imagine a world without tangled cords? No more fumbling for chargers, no more tripping hazards. It sounds like magic, but the science behind it is both elegant and real. You might already be familiar with inductive charging pads for phones, where you simply place your device down and it begins to charge. This works by creating a magnetic field in the pad, which induces a current in a receiver coil inside your phone, like a gentle magnetic handshake across a very short distance. The electrons within your phone respond to the magnetic field, setting themselves into motion and replenishing your device's energy. But the dream stretches further. Scientists are exploring resonant inductive coupling, which allows power to be transferred over greater distances, even across a room. Think of it like two tuning forks, singing in perfect harmony across a space. If one tuning fork vibrates, and another one nearby is tuned to precisely the same frequency, the second one will start to vibrate too, almost as if it's listening and responding. In wireless power, this means carefully matching the electromagnetic frequency of the sending coil with the receiving coil. This sympathetic vibration allows energy to leap across a gap of several meters, quietly and efficiently. Imagine your electric car charging silently in your garage without ever needing to plug it in, or tiny sensors in your home being powered perpetually without batteries, drawing energy from an invisible, gentle current flowing through the air. It's like creating an invisible bridge of energy where electrons can dance from one point to another without the need for physical wires. Now, let's turn our attention to the very way electricity flows through our cities and homes, the smart grid. For decades, our electrical grids have been largely one-way streets, delivering power from centralized power plants to our doorsteps. But imagine, if you will, a vast interconnected web of whispers and responses, where electricity itself becomes intelligent. The smart grid is precisely this: a sophisticated network that uses advanced sensors, digital communications, and two-way information flow to manage electricity distribution more efficiently and reliably. It's like turning a simple road into a bustling, intelligent highway system where every vehicle knows its optimal path and can communicate with the central control. With a smart grid, our homes and appliances become active participants in the energy story, not just passive consumers. This is where the whole Internet of Things, IoT, dances gracefully with electricity. Imagine your smart washing machine deciding to run its cycle not when you press the button, but when electricity is cheapest and most abundant from renewable sources, having communicated directly with the grid. Or your thermostat gently adjusting temperatures based on real-time energy prices and your personal comfort preferences. This continuous flow of data allows the grid to self-heal after outages, integrate vast amounts of renewable energy from diverse sources, and balance supply and demand with unprecedented precision. It's like a vast, synchronized orchestra, where every instrument knows its part, and the conductor, the smart grid, ensures a beautiful, efficient symphony of power flows through our lives. Finally, let's consider something truly remarkable: capturing energy from places we often overlook, heat that simply dissipates into the air. This is the realm of thermoelectric materials. These clever materials possess a magical property. They can directly convert a temperature difference into an electrical voltage, a phenomenon known as the Seebeck effect. Imagine one side of a material being warm and the other side being cool. The electrons on the warmer side gain more energy and move more vigorously, pushing towards the cooler side. This slight imbalance creates an electrical current. It's like tiny, clever sponges soaking up forgotten warmth and squeezing out a trickle of electricity. Think of all the waste heat generated by car engines, industrial factories, or even our own bodies. Thermoelectric devices could capture this escaping energy and turn it into usable electricity. Imagine your car recovering some of the heat from its exhaust to power its own systems, reducing fuel consumption, or tiny devices powered by the warmth of your skin, constantly generating enough electricity to run without batteries. These silent, elegant converters are like gentle alchemists, turning the subtle difference between warm and cool into the invisible flow of power that lights up our modern world. They remind us that energy is everywhere, waiting to be politely coaxed into usefulness. These emerging electrical technologies, from the steadfast security of solid-state batteries to the invisible ballet of wireless power, the intelligent symphony of the smart grid, and the quiet alchemy of thermoelectrics, are not just scientific curiosities. They are the gentle threads weaving a future where electricity is not just powerful, but also smart, sustainable, and seamlessly integrated into the very fabric of our lives. They promise a world where our energy systems are as resilient and adaptable as nature itself, humming along with a quiet, efficient grace. These innovations remind us that electricity's story is still being written, quietly evolving as we sleep, ready to awaken with us into a brighter tomorrow. My dear little one, as the day's bright tapestry gently yields to the soft embrace of twilight, and as the world outside gradually settles into its peaceful, hushed slumber, we too can allow our minds to drift. We've embarked on a remarkable journey together, haven't we? A quiet exploration into the heart of something truly extraordinary, something that, despite its profound power, moves and works with elegant, almost imperceptible grace. We have been whispering about electricity. We explored it not merely as a sudden, startling flash, but as an invisible ballet, a constant, ceaseless dance of tiny, unseen messengers forever in motion. From the grandeur of lightning in the sky to the gentle glow beside your bed, we traced its many forms. Those majestic, crackling bolts of lightning, arcing across the darkened canvas of the heavens, were a powerful declaration of its magnificent presence. And even closer, hidden deep within us, an intricate, subtle current, allowing the gentle rhythm of our hearts to beat and the delicate flow of our thoughts to weave their patterns. Such profound wonder to consider this vibrant energy dwelling within the very essence of everything that is. With quiet persistence, humanity learned to unravel this secret language of energy, inviting it cautiously into our lives, guiding it through hidden pathways into the warmth of our homes. Imagine the intricate network, the unseen threads that weave through sturdy walls and beneath the quiet ground, much like a gentle, tireless river, patiently guiding its light and warmth directly to your very own bedside. It's a truly marvelous thought, isn't it, my little dreamer? This invisible hum, this omnipresent, quiet companion that makes so many precious things possible. The soft, reassuring glow of your nightlight, standing sentinel against the shadows, gently chasing them away. The subtle, comforting whir of a fan on a warm night, stirring the air with a soft sigh. The enchanting stories that flicker and unfold across a screen, inviting you into worlds unknown. All of it, every quiet marvel, is a testament to the persistent, benevolent flow of electricity. It asks for nothing, yet bestows so much, working tirelessly and discreetly in the background, a silent, faithful guardian of our comfort and our dreams. We don't often perceive it, do we? This constant, ever-present companion. It is like the very air we softly breathe, or the steady, dependable turning of our earth. Always there, always flowing, making the intricate machinery of the world function in its own quiet, utterly reliable way. It never boasts. It never demands attention. It simply is. It illuminates our world not just with physical radiance, but with the quiet, reassuring promise of connection, of warmth, of peace. It is the silent, profound magic that allows families to gather, beloved stories to be told, and sweet lullabies to be softly sung in a room bathed in a gentle, ambient glow. Think of it, if you will, as a vast river, peaceful and deep, winding through the expansive landscape of our modern lives. It originates from places of immense, distant power and travels, entirely unseen, until it lovingly reaches the quietest, most intimate corners of your own home. A magnificent journey, undertaken every second, without fanfare or fuss, just a continuous, gentle motion, a quiet, yet profound testament to a world built on intricate, beautiful, and utterly dependable connections. And now, as you lie here, nestled safe and warm in your bed, bathed in the soft, hushed quiet of the night, you can almost feel that gentle, pervasive presence. The barely perceptible hum from beyond your window, the reassuring glow from a distant street lamp, the sleeping devices scattered around your room, each holding their own tiny, slumbering currents within their silent circuits. It is a lullaby, isn't it? The electricity, ever flowing, ever ready, but now content to simply be, to let the world and you softly rest. It is a story of constant, unseen motion, of silent, unwavering service, of invisible, profound grace. And in that grace, that quiet constancy, we find a deep and abiding peace. We discover profound wonder in the thought that something so powerful, so fundamental, can be so softly and so quietly woven into the very fabric of our everyday existence. It is a profound mystery, yes, but a beautiful and reassuring one. This intricate dance of energy, this silent, life-giving breath that animates so much of our vibrant, waking world. But now, even electricity itself seems to gently temper its vibrant pulse, gradually slowing its energetic pace to match the serene, gentle rhythm of your own slowing breath. The day's active, bustling currents begin to softly diminish, becoming quieter, more contemplative, mirroring the stillness that settles over the earth. The world outside, now lovingly bathed in the ethereal silver glow of the moon, rests. And so, my precious one, should you. Close your eyes, little scientist, and let your spirit soar. The magnificent journey of electricity, like all great journeys, never truly ends. It simply transforms, continuing its flow in different, quieter ways. As you gracefully drift into the boundless realm of dreams, that gentle, invisible current continues to flow, perhaps finding its way into the quiet hum of your imagination, or in the gentle pulse of your own sleeping heart. It will be there, waiting, a faithful, patient guardian, when the first blush of morning light softly awakens the world once more, ready to continue its quiet, dependable, and essential work. For now, let the comforting thought of its steady, silent flow bring you a profound sense of peace. Let it softly remind you that even the most powerful forces can be gentle, reassuring, and a part of the quiet, comforting stillness that settles over the world as you sleep. May your dreams be as bright and tranquil as the softest, most tender light, and as deep and calm as the unseen constant currents that flow ever so gently all around us. Sleep well, my little wanderer. The wonders of the universe, both seen and unseen, will be patiently waiting for you gently when you awaken. Sweetest dreams.